Hi, how you doing? Welcome back. Today we're going to look at trigonometric identities and then integrating those. Okay. So what you see is the list of standard integral results from the beginning of the chapter, and you've been using some of those already. So we'll just focus on the trigonometric ones. Okay. So I'm just going to look at these ones here. Okay. If the integral is already of the form either sec squared x or cosec x cot x or cosec squared x or sec x tan x, they're no easy. You can just apply one of those standard rules. However, sometimes they're not in that form. Okay, and you've got to look out for when that happens. What I'm going to do is I'm going to talk you through the examples from your textbook on using trigonometric identities with integration. All of this integral work is extremely important, of course. So I can't really understate just how important it really actually is. Okay, you need to know the identities inside out, because if you don't, you're not going to be able to integrate some of these questions you asked. So let's crack on then with the first one. So example 5 is integral of tan squared x dx. Okay. Let's just go back to that list again. You'll notice, see, tan squared x dx is not there. Okay. But what I'm hoping you're going to pick up is, if you just look through the list, this one here, number 6. Okay. I'm hoping that you remember there's an identity that relates tan squared x and sec squared x. So if you can actually get your expression in terms of sec squared x, you can use this result. And that's pretty much your method for a lot of these integration questions that we're going to do. Okay. Now, if you cannot remember the identity, here's just a quick reminder. Just to begin with, the one that you all remember, sine squared x plus cos squared x equals 1, and then to get tan squared x, you divide throughout by cos squared x, so you get tan squared x plus 1 equals sec squared x. And there it is. Okay, so you rewrite the question as integral of sec squared x subtract 1 dx. Okay, and then once you've written that, you can just apply that standard result. The integral of sec squared x is tan x, and then integral of negative 1 is negative x, and then plus c. And that's all it is. Okay, just a one-step question really before you write down the answer. All right, let's move on to the second one then. Next example is this. So integral of sine squared x dx, and then you've got some limits to put in. Okay, well, sine squared x, this is a really common one. Okay, another common one is integrate cos squared x. It's a really common one. Let me just tell you of a common error. Okay, a common error is to think, oh yes, I know that. That's going to be cos squared x, because when you integrate sine, so what happens with cos, isn't it? Okay, let's just forget whether it's positive or negative for the moment. That's not important. Let me just explain to you why the answer is just not going to be cos squared x. Okay, when you differentiate this, you see, okay, what are you going to get? Are you going to get sine squared x? No, of course you're not. Okay, you're going to do 2 cos x, and that's power 1, of course, sine x negative. That looks nothing like sine squared x, is it? Okay, and similarly, if you try and think the answer is sine cubed x, no, that's not going to happen either. Because if you try and differentiate sine cubed x, you're going to get 3 sine squared x cos x. Okay, so what I'm saying is you need to use an identity here. What's making it difficult is the power. Okay, it's the power of 2 that makes it a bit harder. Okay, now what you need to do is look for an identity that involves sine squared x. Okay, now you might think, oh yes, it's 1 minus cos squared x. Well, integrating cos squared x is very similar to integrating sine squared x. Okay, you can run into a similar difficulty if you don't use the appropriate identity. So if you just recall all of your identities, eventually you'll get down to this one. Okay, that I'm writing up here. You get down to cos 2x is equal to 1 minus 2 sine squared x. Okay, and use that one because obviously the sine squared x can then be rewritten in terms of cos 2x, and integrating this one, cos 2x, is not a problem. Okay, so let's just rearrange that. So you'll have 2 sine squared x is equal to 1 minus cos 2x, then divide by 2 you'd have sine squared x is equal to a half, subtract a half, cos 2x. Okay, and so our integral here just becomes integral, better put in the limits, pi over 8, pi over 12 there, and in brackets 1/2 subtract a half cos 2x dx. Okay, there we go. And then we're ready to integrate that. So first term is just going to be 1/2 x, and then I'm hoping you're getting used to these by now. It's going to be -1/4 sine 2x. Okay, if you're not sure about that, -1/4 sine 2x, just pause the video and try and get to it. Okay, at this phase with these standard integral results now, I'm not giving that much explanation with them because I want to crack on with the new bits, as it were. And then we've got some limits to substitute in, pi over 12 there, pi over 8. Okay, so let's just do that. So pi over 8 first of all, so half of that is going to be pi over 16. Okay, and then subtract 1/4, and I better write it in, I suppose, sine pi over 4. So that's the first limit, and then subtract, put in brackets, as I've said many times before, if you've got more than two terms. So that's going to be half of pi over 12, so it's pi over 24, and then subtract 1/4 sine, and that's going to be pi over 6. Okay, let's just work out what they are. Okay, so pi over 6, if you want you can subtract pi over 24 straight away. Sorry, pi over 16, subtract pi over 24, you can do that straight away if you want. So I think that's going to be 3 pi over 48. Let's do the denominators first. Okay, and then this one in brackets here, that's going to be 2 pi over 48. Okay, then we're ready to subtract them. This one, -1/4 sine pi over 4, that's sine 45 degrees, that's root 2 over 2, so times by root 2 over 2, and then this last term will be plus because of the brackets, and that's 1/4 multiplied by sine pi over 6, sine 30 degrees, that's 1/2. Okay, so that's that. Let me just create some more space so I can continue writing down the solution here. Let's just go up to the top here. Okay, so the 3 pi over 48 subtract 2 pi over 48, that's just pi over 48, so that's that one. And then better simplify the second term, so that's going to be subtract root 2 over 8, and then we're going to have plus 1 over 8. And so you can leave your answer like that if you wish. So pi over 48 subtract root 2 over 8 plus 1 over 8. Okay, there's no real need to write down this line I'm writing down now, pi over 48 plus 1 minus root 2 all over 8, as long as you can see they're exactly the same. If the question just asks you to evaluate, then what I had at the top there will be fine. Remember in the exam sometimes you push for time, and so unless you're asked to write it in a particular form, you don't need to. So hopefully you're okay with that one. Maybe before I go over the next example, I'll just take the opportunity to mention the other integral you're often asked to evaluate, that is cos squared 2x. Okay, here you need to look for the appropriate identity, and the appropriate identity is this one written up. Cos 2x is the same as 2 cos squared x subtract 1, and hopefully without me going over it you can see what to do. You just rearrange this identity in terms of cos squared x. You can then rewrite this integral as something involving cos 2x, and then it's easy to integrate. Okay, try and remember those two results. These two types of integral, they come up a lot. Okay, they come up a lot, and just memorizing the set method for each of those is vitally important, I would say. Okay, the key thing is that you're always using one of those, the identity for cos 2x. It's either going to be in terms of cos squared x or sine squared x. Okay, right. Of the examples I'm going over in this lesson, those two there up at the board, they're probably the most important. Okay, So it would be my advice that when you're revising for exams, you look at that video again. Right, next is this one. Now I'm hoping you're thinking, oh yes, I know what identities come up here. It's the identity for sine 2x, okay? 2 sine x cos x. And if your mind did not think of that as quickly as I said it, then you need to raise your game a little bit, okay? Because you need to recognize when you've got the product of sine x and cos x and that the angles are the same, then you're often going to use this identity here that I've written down, okay? So just try and look out for that, okay? Right, let's go. What we don't have, of course, is we don't have the same angle, and we don't have the half, so we don't have the 2. So I'm just going to rewrite that first of all as 1/2 sine 2x is equal to sine x cos x. So that's just looking a bit closer to the actual integral we're asked to do. And I'm just going to change the angle from x to 3x. So that's going to be sine x is now sine 3x and cos x now cos 3x. And it's called the double angle formula for a reason. We're just going to double this angle here on the left hand side. So what that means is our integral is in fact going to be this here, 1/2 sine 6x dx. Okay. Some of you are going to be able to go straight from the question to what I've written down here without the need for writing down this. Others are going to have to just do extra work in, okay? Notice there's only one method mark generally for this. That's through the use of this identity. And once you've used it correctly, you get that method mark, and then the next mark is going to be for writing down what your answer is. So hopefully there's no explanation needed. It's going to be negative 1/12 cos 6x plus c. That is it. As I said, if you're not sure about why you've got the negative 12th there, just go back to some of the previous sections, okay? Because by now that has got to be common knowledge. Right, moving on. The next example is this one here, sec x plus tan x all squared. When you have, here's a tip for you, when you have an integral like this, you're going to need to expand the brackets, okay? You'll notice of all the identities that we're using, none of them are in the form of 2 different terms or more all squared, okay? So you'll have to expand the brackets, right? So let's just do that quickly first of all. So you'll have sec squared x plus 2 sec x tan x plus tan squared x dx. Now, as I was writing that out, I'm hoping you're thinking, oh yeah, first term, great, I know how to do that. Then second term, you're thinking, not too sure. But actually, if you look at the standard results on the first page of the chapter, you'll see it's an easy one. Okay, and then the third one, well, we did that earlier, didn't we? Okay, it's the first one I looked at today. I looked at integral of tan squared x, so we can do that one. So actually, just by expanding brackets, it's going to make it quite a simple one to do. Okay, so the first one, the obvious one is that sec squared x. When you integrate that, you get tan x. So that's one of our standard results. We learned that right at the beginning. Okay, then the second one. Okay, so the idea here is that you need to know that when you differentiate, let me write it down. When you differentiate sec x, you get, pause, do you remember? Or have you looked it up? You get sec x tan x. Okay, so if I just put a 2 in the front of both of those, that is now a correct statement. Okay, so this second term will integrate to get 2 sec x. Okay, and the last one, tan squared x, well, we've done that. Okay, if you just look back to what the answer was, it was tan x, subtract x plus c. And let me just get rid of some of that so it looks a bit clearer. Okay, you can simplify that a little bit, so let's just do that. Okay, we're going to get 2 tan x plus 2 sec x subtract x plus c, and that is it, done. Next I'll suggest you work through the the third exercise, that is exercise C, and try and do as many of those as you possibly can, using the answer in the back of the book to check. Okay. Right. Hope you enjoyed that one, and I'll see you again. Bye bye.